Hello, students. Video is to briefly go over the problems that you've seen. The uh, this is the circular motion homeworks and the uh, forces homework that y'all should have. The college physics and the university physics should have the same problems in general. They're in different forms, obviously. Some of you have WebAssign, some of you have a printout. And so we're going to carefully go through these problems, and we're not going to go and do every step. I'm just going to outline the sort of things that you should see. Okay. So, if I go through these first problems, this is all going to be circular motion stuff. So let's look at those notes for a minute. All right. The particular thing about circular motion was that you have a constant speed, and it's based on the periodic motion of a thing going in a circle. All right. So the idea is that if it goes around the circle once, it takes some time t, which is the period, and it goes a distance 2 pi r, where r is the radius. So you're going to have this formula, which is going to tell you the speed based on the time and the size of the circle. And sometimes you're going to be expressing things in terms of a frequency, how many circles per minute or how many circles per second. You have to convert that to the period. How long does it take to actually do one of those circles? All right, so there were some practice problems that you've seen here in the notes. In particular, converting revolutions per minute to a period is kind of important. And then finding the speed, all right, finding V using R and T. Then this is the bit where, in that bit of the circular motion activity from, I think, last Friday, this is the bit where you were drawing the radiuses and the velocities. And if we step through it, at some moment you have the radius and the velocity. At some later moment you have a final position, a final radius and velocity. These radiuses are the same, and these velocities are the same by definition. It's uniform circular motion. So the velocities are the same, the speeds are the same, the directions are different. And so the idea was transporting these vectors to the same location. Right? So there's V initial. And it's the same direction as V initial at the top of the circle. But now we've drawn a delta R and a delta V, and those are similar triangles. So that we know that not only are sides of these triangles the same in the sense that they're isosceles triangles, but we know that ratios between the sides are the same because they're similar. So delta R over R equals delta V over V. And this delta V, if we put it halfway between V initial and V final, where the little hand symbol is, you note that it points towards the center of the circle. And it will always point towards the center of the circle, no matter how we draw this angle. Except for the bit, if you was exactly 180 degrees apart, it would be difficult to do triangles. But you would have delta V would go to the left, and halfway in between would be here, and it'd still be towards the center of the circle. So the drawing with triangles is supposed to be on smaller angles. So that's the important bit. Because delta V is towards the center of the circle, you have this relationship. Delta R over R is delta V over V. And if we divide by delta T, what we have is, the left side is V over R, and the right side is A over V. And so we rearrange it, we get the acceleration. These formulas that we've seen in the boxes are basically the only formulas you have. A is V squared over R, and V is 2 pi R over T. And that's all you should need. That and converting from RPM to a period. All right, so we do an example problem. If I give you the radius and I give you the lap time, the period of the motion, can you get the velocity and the acceleration? Well, the velocity is just 2 pi over t, and the acceleration is v squared over r. And you could, in principle, find the acceleration as a function of the period. You could just plug in 2 pi over t squared over r, and you would get the same, you'd get a formula that makes sense. But oftentimes it's easier just to go in steps, find the velocity, and then the acceleration. And so in these problems, all right, so we don't need the mass. We're not cared about that. But we care about the radius, and we have the speed, so v squared over r would give you the acceleration. In problem number 2, the revolutions per minute you convert to a period, right? And one revolution is 2 pi r, and you're told the radius, and then convert minutes to seconds. And so you can get a period out of it. Follow the notes on converting that. And then the speed, v is 2 pi r over t. The acceleration is a is v squared over r. And the direction is always going to be towards the center of the circle. In this case, towards the center of the wheel. So here, for number 3, we go in the other direction. We give you a radius, and we give you the acceleration. The free fall acceleration is basically due to gravity, and it is towards the center of the Earth. It is your centripetal acceleration. And so, can you get the speed from the acceleration? Yeah, a is v squared over r. And then can you get the time, the period, from the speed? Yeah, v is 2 pi r over t. Right? So these questions should be reasonably straightforward. Now, the other questions that you see, this is the second assignment. For 201, it's optional, and for 231, it was the second web assignment. Right, you've seen these things. For problem 1, it's regular a is v squared over r, and it's expressed a little differently. You have feet, you have to convert to meters. You have an acceleration, which is in terms of g, so you have to do 19.1 here times 9.8 to get the true acceleration. Right? But once you get the acceleration, you can get the velocity, you can get the period, and then you can convert that to revolutions per second. So, all right, number 1's like that. Number 2, the radius is not obvious. L here is not your radius. You're looking for a thing spinning along the horizontal direction. So your radius r is like L sine theta over 2. Right? Is it, you can figure out what the radius of this circle is from the geometry of the problem. And given a speed, can you figure out the acceleration from that? Given the speed and the radius, can you figure it out? Yeah. A is v squared over r. So figuring out the geometry in this problem. Okay. All right, so 3 and 4 were all about finding the total acceleration. And in 3, it's finding the portions, the part that's into the circle that causes the turning, and the part that's tangent to the circle that causes speeding up and slowing down. Right. So we give you the total. You just find the components of the acceleration based on this angle, right? So the radial acceleration is the adjacent component, so it's cosine of theta, and the tangential acceleration is the opposite component, so it's sine of theta. Right? So you're just finding the components there, and then once you have the radial acceleration, can you get the speed? So for number 4, you're going to have to get the tangential acceleration from the fact that it slows down. You have a speed in kilometers per hour, but it goes to a different kilometers per hour. So you have to do unit conversions to meters per second as well. Do the unit conversions, and then you have that it changes speed over time. That gives you the tangential acceleration. And then from the radius and the speed at a particular point, you get the radial acceleration. All right, that's A is v squared over r. And so you get the two components. Can you find the length and direction from two components? And when you find the direction, it's going to look like something like the picture number 3, except the velocity is going to go in the opposite direction. Right? Is it the acceleration vector will be sort of behind the radius, opposite the direction. Remember in the lab, we went over when is a thing turning, speeding up, slowing down. Right? So number 3, this is an object that is speeding up and turning, because the acceleration has parallel and perpendicular components, and it is sort of in the direction of the velocity. For number 4, if you drew a similar circle, the acceleration and velocity would be in sort of opposite directions, and so it would be slowing down and turning. Right? And so carefully go through those. And again, this is do your best at it, see what you can do with it. All right. And so now, the other thing that you've seen so far is this forces thing. And this is an assignment that is mostly about Newton's laws and what would be on a free body diagram, which we've just went over in a previous video. So you want to be careful of, in a sense, make sure you're watching the other videos as well. The other recent videos, the stuff I'm sending you in the email today. But I'll go briefly over these. Number 1, if you're told what a constant speed, do you know something about the acceleration? And then if you know that about the acceleration, what do you know about the net force on an object? All right, so remember, let's go over Newton's 3 laws. Let me pause for a second. Okay, so remember, Newton's first law is a statement about how the velocity changes when there's a force. If there is no net force on an object, the velocity is constant. And that works the other direction. If the velocity is constant, there must not be force. Right? That comes from kinematics and what will eventually be Newton's second law. If the velocity is constant, then the acceleration is 0, because delta v is 0. And the acceleration is going to be a function of the force. It's going to be the force divided by the mass. So let's go down to Newton's second law here. When there is a net external force on an object, when you can identify a net force, the acceleration caused by that net force will look like the sum of all the forces on the object by the mass. So you can say that a couple different ways. You can say the acceleration is the net force divided by the mass, or you can say the net force is the mass times acceleration. And the key sort of thing is that when you add up all the forces, that tells you the direction of the acceleration. And the size of that net force is the mass times the acceleration. So, number 1 is a question about Newton's first law. How is the force, what do you know about the force if the speed is constant? And it's in a constant direction, so it's not circular, it's going in one direction with constant speed. So number 2 is talking about equilibrium, which we kind of talked about in previous videos. Equilibrium is that the acceleration is 0, and that is telling you something about the forces. It also tells you something about the velocity. Right? So If the acceleration is 0, is the speed constant or does it change? Does the object need to be at rest if the acceleration is 0? Being at rest means the velocity is 0. Does it need to be 0? Right? Again, if it's in equilibrium, is the acceleration 0? If the object's in equilibrium, does there need to be two forces on an object? Right? One would not be in equilibrium, but there could be 0 forces. There could be more than 2 forces. And then, what does equilibrium mean? Does it mean, what does it mean about the net forces? Which, if you've been listening carefully, I've kind of given you the answers to this. But number 3 is a question about the friction force, which you can kind of gather from the forces activity video and the forces activity we talked about. Friction forces look like something having to do with the normal force, but it also has something to do with the forces being in equilibrium. Right, so if a crate's stationary on a ramp at some angle, is it necessarily equal to mu times n, or could it be just whatever it needs to be to make the forces in equilibrium? Do we know anything about the gravitational force acting down the ramp, that component? Or and you go into that app with the block on a slope, and there's let's see if I can pull that up. Do I have it open? Where is it? I had it here. Let's open this up. All right, here where it says show gravity components, if you click that, it shows the components of that weight force along the ramp. And that sort of indicates a little better what I mean by splitting that up into components, and you should try that. In fact, let's do that. Let's see if I can actually make this open. All right, so here we are. We're going to change this angle. We don't really care. I'm going to freeze it there. Now, if I show gravity components, you see now there's 2 additional arrows. One in the y direction, which is, we can say this angle in here is about this 14-degree angle that is adjacent. So this part will be cosine of theta. And in the very small angle here, let me hide and show. You can see where they're flashing. That angle there is opposite the angle, so sine theta. So, it was this one, right? So, can I know anything about the part of the gravitational force ramp? Can I know how that relates to the friction force? Or, is it greater than? Is it less than? Is it equal? Can I know anything in relation to? Oops. Number 4 is the same sort of thing. How can I identify the forces on an object? That's the sort of thing. Free body diagrams should only have forces, and they should only have forces on the object that's of concern. Right? So they shouldn't have forces by that object. They should have forces on that object. Right? So you can look through these. Is the force exerted by the object on that object? Is the force from the incline on the object? Is the net force a force on that object? Right? Is the gravitational force a force on that object? You go through these and you can quickly say, well, these forces are on the object. These are not forces, or they are forces not on the object. All right, so number 5 is a lot like number 1. You're told that a thing moves at constant speed. What do you know about the forces? In this case, what do you know about the accelerations, and how does that relate to the net force? When you say total force, it means net force. Right? So 1 and 5 should not require, if you think about it, should not require actual calculation. It requires reasoning. Number 6 here, and if you're doing the web assign, that will be there will be a number 7 as well. Those things do require reasoning and doing calculation. I tell you that F1 here is 35 newtons and F2 is 16 newtons. And we have 2 cases. Part A is doing it when there's a 90-degree angle between them. So you put F1 along the x-axis and F2 along the y-axis. And so they each have one component. F1 is in the x direction, F2 is in the y direction. When you add those, you have 2 sides of a triangle, and you're trying to find the hypotenuse. Part B is put F1 along the x-axis. F2 now has 2 components. It has a sine component, which is in the y direction, and a cosine component in the x direction. Find those, and then when you add them, you add the x direction stuff, and then you separately add the y direction stuff. So you'll have like F1 plus F2 cosine theta, and then F2 sine theta. You still have the net force is 2 components in different directions. They're 2 sides of a triangle. Can you find the length and direction when you have 2 sides of a triangle? So those are the things I wanted to go over in these videos and these problems. And that's probably all that I have time for right now. If you have specific questions on things that you've seen, please send me an email and we can go over them in the Saturday session. I can record a video and give it to people. I can go over it the next time I'm in class. These are things where we can go over them carefully. What I want you to do with this stuff that you've seen so far is do your best work on it. Think about what's going on. Read the text, read the notes, look through the videos I've done. Come up with questions, or try to answer these to the best of your ability, and we will go over them in detail. The circular motion stuff should have been simple enough that you can finish it. But if there's a detail that you need to go over, we can go over it. And we want to start doing forces in earnest next week. Again, if you have any questions, email me. Take time during the Saturday session to talk with me. And we will go through and figure out what's going on with these things. And this is a sort of thing where I've heard a lot of, I'm having difficulty with the forces activity, or I'm having difficulty with particular sorts of, how do I do this? Not so much questions focused on what is the goal of this question? What do I need to do in it? So if you have a specific question, get those to me, and I'll try to answer them in some satisfactory way and share it with the class.